Okay, so welcome everyone to this tutorial today, which will be about ab initio molecular dynamics mainly. And as Basti already said, I'm Mariana Rossi, and I work currently at the Max Planck Institute for the Structure and Dynamics of Matter in Hamburg. So I'll tell you two things. The first is that if you find anything you want to ask, please leave it to the end of the talk. Just so that we can have a recording all through the talk, right? But the other thing is that if we want to discuss something and we find something not so correct in the slides, we can also do a correction in real time so that in the end you have the material that we discussed in this tutorial fully with annotations as well. So without any more to say, I will start by telling you the approximations that the main approximation that we need to do in order to talk about ab initio molecular dynamics, which will be essentially about how nuclei move in some potential energy surface. Okay, so if you start from the Schrödinger's equation, which here I show in the time independent form or the time dependent form, you have in principle this wave function psi here that depends on all the degrees of freedom of both electron and nuclei in this Hamiltonian that is in principle your many-body Hamiltonian. So the underlying approximation that we'll need to use in order to talk about ab initio molecular dynamics is the Born-Oppenheimer approximation, in which you effectively decouple the dynamics of the electronic and the nuclear degrees of freedom. I will not go into details of how you derive these. I think most of you have seen this in textbooks, but I'll just refresh your mind about the central assumptions that happen. So what happens when you do this approximation, right? So at first you would have atoms here that are electrons with nuclei together, right? But then you do this Born-Oppenheimer approximation, and what happens is that you now have two systems, a system of nuclei and a system of electrons, and these nuclei, they define this external potential which you use in order to solve your electronic structure problem, in order to find the ground state of the electronic structure problem, and at the same time this ground state will define the Born-Oppenheimer potential in which your nuclei can move. Right, so that's what you end up with. And further to that, I would like to remind you that the Born-Oppenheimer approximation doesn't really say anything about how you treat your nuclei, whether they are quantum particles or classical particles, like I show here. You have a freedom to choose what you do with them after you do this approximation. And further to that, you also have a freedom to choose what type of forces you apply to them, if you really take them as being the gradient with respect to positions, which in the start of my presentation would be Q, or positions here for me, of this Born-Oppenheimer potential energy surface, or if you do a harmonic approximation around a certain potential well. So here today in this talk, what everything we'll be talking about, the realm of ab initio molecular dynamics, concerns classical nuclei, right, moving in this fully enharmonic potential with forces coming from the Born-Oppenheimer potential energy surface. All right. Then how does this actually look like? So you have classical nuclei now, and the classical Hamiltonian is given by this expression that you have here above. P are my momenta in this case, Q are my position, this is my Born-Oppenheimer potential, and M would be just the mass of the nuclei. And in order to motivate some of the powers of molecular dynamics in general, I would like to tell you a little bit about probabilities and probability distribution and why we can use molecular dynamics in order to explore some thermodynamic properties of systems. So if you are in the canonical ensemble, for example, where a number of particles, volume, and temperature are held fixed, you have that the probability distribution, the probability function defined in this ensemble is given by this e to the minus beta h. Beta is the inverse temperature, 1 over kBt, over the partition function z, which is classical mechanics. So it's nicely given by this integral over moment and position of minus beta times your Hamiltonian, right? And what you quickly realize is that in classical mechanics, position and momenta are not correlated, Interesting. I changed the slide, but the slide didn't change. Let's see. Yeah. Okay. Position and dynamic are not correlated. And so you can factorize this probability distribution into one corresponding to the momenta and one corresponding to the positions. And they look like this blue and red term that I show here. Now, what you see is that the blue term is actually quite easy to calculate, okay, because it's only quadratic in the momenta. This is a Gaussian integral, and this part here is also trivial. While in general, the red term is quite difficult to calculate because you don't generally know how the potential depends on the positions. It might not have an analytical form. I mean, you really don't know. However, this term is really very important because most of the observables we are normally interested to calculate a thermodynamic average on. This symbol here is a thermodynamic average. They are depending on the positions of the nuclei of your system. Okay. And when you write down the simple expression of what you would do to calculate in thermodynamics, in statistical mechanics, sorry, this quantity here, you would have an integral over this probability distribution times your observable A here that depends on Q. And it's easy to show that only the red term survives in this case. The same would be if you would be looking at time-dependent property, which we won't talk about much today. So what do you do in order to calculate this if you don't know an analytical expression for it, right? Well, you can try, the first thing you can think about is you can try to do what the expression tells you to do. What is this? It's an integral over all the positions of my observable A of Q times this probability distribution. Okay, well, I can actually evaluate each of these terms if I know my potential energies. So if I have a potential energy surface, sorry, I can basically look at it and say, okay, I start, sampling points in this potential energy surface, and the more points I can put on this, then I can evaluate this, I can evaluate that, and eventually I can evaluate an integral if I define a grid that I can sample like that, okay? However, doing this very naive way to do that would scale very unfavorably with the number of atoms that you have in your system, because you would have to do a lot of grid points for each coordinate of each atom that you have in your system in order to be able to perform this integral. Okay, so it would scale basically with the number of grid points G to the exponent of 3n, where n is the number of atoms, right? So it's not practical to do something like that. Instead, it's better to perform some sort of what we call importance sampling. What importance sampling means is the following. You generate many configurations, which I here call QS, according to this distribution P of Q. And then you will be able to calculate this average of your observable by simply summing over all these realizations of your system that you just created that is consistent with distribution, and calculating the average in this way that I write here. So in that case, what is nice is that because you'll be sampling according to this probability, you'll have a lot more points where it's more important for you to sample, and a lot less points where it's not important for you to sample, and you hope that you converge quickly with the number of points, this expression here, right? And in order to do something like this, there enters basically molecular dynamics. So you can look at that Hamiltonian, that nuclear Hamiltonian that I wrote before again. And we all know how to write equations of motion, Hamilton's equations of motion for this Hamiltonian. So this is just textbook. So Q dot is the time derivative of the positions, is P over M, and P dot, which is the time derivative of momenta, is minus the gradient of the potential, which is the fourth, right? Now, you can show that the configurations created by this time evolution are consistent with and conserve this probability distribution. This is very, very easy to show because you can look at the time derivative of the probability distribution, and by using Hamilton's equations of motion, you can show that it's 0, and you can also show that it conserves in the sense that the probability at time 0 is equal to the probability at time t. I won't show this, but if you want, if the interested student can do it, I'm pretty sure. So that's very nice because now you have a way to create configurations that are consistent with those probabilities distribution, right? And then there is a second thing that usually one wants to use when talking about molecular dynamics, which is the ergodic hypothesis, and that is that an ensemble average is equal to a time average in the limit that this time that your sample goes to infinity, because then your system in theory will have time to explore all possible configurations that are relevant. Okay, so within these, with all of these in hand, yeah, and with the ergodic hypothesis in your hand as well, you can now sample. You can do sampling in this phase space that you define by your potential and so on, and calculate the statistical averages by using molecular dynamics. So this means that now, instead of doing all of those point samplings that you had in the previous slide, you will have a path that will start at some point, and then it will sample quite a lot the regions that are very important, and then we won't talk about this, but then you hope that it samples all of them, and passing these barriers is usually complicated, but one can talk about advanced methods. I think there was a lecture already talking about replica exchange and so on that takes care of that. Okay, so now you can calculate things that you can calculate this through molecular dynamics. And what is the main idea of molecular dynamics then? So the main idea of molecular dynamics is that you start your system by assigning initial position and momentum to it. Then you somehow evolve numerically Newton's equations of motion for a finite time increment. And then that will give you new position and momenta with which you can calculate forces and go back to the first step. This, in a nutshell, is what molecular dynamics wants to do with your system. And how to do it and how to do it in different ensembles will be the subject of the rest of this talk. Okay. And also how to do it ab initio, yes. Okay, so first, how do you evolve these with finite time increments? Well, you can first do a Taylor expansion of your positions, right? I mean, this is the order 0 thing you can imagine to do. So you expand around time t with an increment delta t, and then you have this usual Taylor expansion, which I cut after second order. Yeah. And this is a way already to define an integration scheme for your equations of motion, but it's not very accurate for several reasons. One of them is that the error with respect to delta t is already at order delta t to the third, and it will be unstable, the dynamics. So what is usually done in most codes out there nowadays is that you can equally expand back in time your position. So you do a Taylor expansion with minus delta t. You sum those two expressions, and you end up with what I have here in the bottom, in which the error is order t to the 4, delta t to the 4. That is a much more stable algorithm. It's also time reversal, and it conserves the phase space volume. You can show all of that. It's called the Verlet algorithm. And I just wanted to point out that this q dot dot, which is the second derivative of the positions with respect to time, is related to the force, right? So it's the force over m, so there enters the force. This is not exactly what, this is already the Verlet algorithm, and it produces dynamics which are consistent with the more normal way that you see the Verlet algorithm, which is the velocity Verlet. So they produce the same type of dynamics, but normally you actually, for other because of other advantages, mainly not having this t minus delta t, you actually do a velocity relay, which is based on such Taylor expansions of the velocity. And this is the expression that you end up with, right? So you can calculate the velocity at step t plus delta t with the velocity at step t plus this increment. And I'll show in the next slide the full scheme, how you actually do the velocity relay. It's very powerful, this integrator. It's the one that is in most codes out there, including FHI-aims. And it's implemented in detail, like I show here in this slide. So one step, you do a symmetric splitting of this velocity relay. So you don't do a full time step at once. You evolve the velocities at half time step, then the position at full time step, and then the velocity again at the full time step. You can see this from you can see how this splitting comes about from different ways. The most elegant, I think, is with Liouvillean propagation of the dynamics. And I will tell you in the end of this talk some books you can look at for detailed derivations of this type of schemes. So how does it look like? Well, you first evolve the velocities for step delta t over 2. As I showed in the previous slide. Then you evolve the positions at step t plus delta t. What will that be? That will be the positions at step t, the step before, plus the velocity that I just calculated at step t plus delta t over 2 times my time increment delta t. With that, I have new positions, so I can evaluate new forces at t plus delta t from these positions. And with these new forces, I can finalize my evolution of the velocities at the full time step, which is the one that I had here before, plus these new forces over the mass times delta t over 2. And then at this point, you can compute any instantaneous properties at step delta t because you have both velocities and positions aligned at the delta t. And then you go back to the beginning. You don't need to calculate the force again at this step because at the next step, this force t plus delta t becomes this f of t. So you have only one force evaluation per step of the scheme. So that's it. And that's how you will then evolve in time. You have to choose delta t. I'll talk about that. And you have to somehow evaluate the forces from this position. And that is where most of the science goes into if you're talking about ab initio MD, because you have to calculate an ab initio forces, right? So this line that I had there, evaluate f of t plus delta t from q of t plus delta t, involves evaluating an ab initio force. What does that mean? It involves calculating the gradient minus the gradient of this minimized energy, which in DFT would be finding the density that minimizes this energy functional of the density here. No? So it involves solving the full electronic property, the electronic problem at those fixed positions of the nuclei at that time step, and also calculating these forces in an ab initio code may not be so trivial, or is usually not so trivial, because of the full architecture of codes that we have. And I talk about a little bit what we have in FHI-aims. Yeah. So in FHI-aims, we have at least a few terms that enter these forces. I will talk about a few of them in more detail in the next slides. So you have the force is given first by this Hellman-Feynman term, which is the one you would expect to have in any type of electronic structure calculation. But this is not all, and it's known since a long time that calculating only this term in basically all code architectures does not give you forces that you can use in any way. So because of the basis sets that are used in FHI-aims, a very important part of the force are the Pulley forces that include also corrections for GGA, meta-GGA, and relativity. There is another piece that is a term that is related to the lack of full self-consistency of your solution, the self-consistent solution of the electronic problem. There is another term which is the multiple given by the multiple expansion of the Hartree potential, And you should know that everything you add to your problem will add a term in the force. So if you have the van der Waals corrections, there will be a term coming from the van der Waals correction, the exact exchange, there's also forces related to those. And anything you add, basically, you have to be very careful that you have to calculate forces related to those terms. So let's look a little bit how they look like, these terms. So it's easier to see how these terms look like if you actually look at the energy expression that you use in FHI-aims. This is the Harris functional. So the energy functional is written as a sum over the occupation numbers F and the Kohn eigenvalues, minus half here, rho is my density, and nu H is the Hartree potential. Nu XC is the exchange correlation potential, EXC is the exchange correlation energy, and this ENN is the energy of repulsion between the nuclei. The forces, as I said, will be the variation of this energy functional with respect to nuclear positions. And here I have a big disclaimer to do. Until now, my positions of the nuclei were Q. But it's historically the case that molecular dynamics world tells everyone that the notation is such that Q are the positions of the nuclei, and the electronic structure says big R are the positions of the nuclei. So my slides are consistent with these two schools of notation. So this is equal to Q in my presentation, but it's also, it can be confusing in an electronic structure because Q is the charge. So anyway, so R is, in this case, is here in the electronic structure problem, the position of the nuclei. And then the Hellman-Feynman forces come from the fact that you can write these electronic, the Kohn eigenvalues, sorry, as the expectation value of the Kohn Hamiltonian and the Kohn orbitals. This epsilon is like this epsilon, I'm sorry. And then you see that the Hellman-Feynman term is simply this one. So it's the explicit derivative of that term with respect to nuclear positions. So you have a term coming from ENN, and you have a term coming from the external potential that is coming from this Hamiltonian. Doesn't appear exactly here, but if you write the expressions, it's easy to see. So this is the Hellman-Feynman forces. They are quite straightforward. They are nice, but then comes the other terms, right? So the Pulley forces, they come from these other part here. So if you do the variation of the Kohn eigenvalues, you have the first term that gives rise to the Hellman-Feynman forces. That's the variation of the Kohn Hamiltonian, and then you have these two extra terms which relate to the variation of the Kohn orbitals here with respect to nuclear positions in this case. These terms, these two terms that I have here in orange, they would be zero in the complete basis set limit, even for an atom-centered basis set, but that's in practice never achieved. They would actually also be zero if you would include explicitly the derivative of the basis functions in the basis functions itself, but that's not practical to do. What is much more practical to do is to explicitly calculate these terms and add them to the forces. And you have to be a bit careful how you do that. You have to use, so this is the basis set expansion, right, that you normally see. So these are my Kohn orbitals. They are expanded as a set of coefficients, and my basis sets here phi. You have to use the generalized eigenvalue problem that you have in this case. S mu nu are the overlap of the basis set, and you also have to impose that the norm and the orthonormality of the Kohn orbitals is maintained as you change your nuclear positions, and then finally you get to this expression that I show here. So these are the Pulley forces. So this is my occupational numbers again. These are the expansion coefficients of the Kohn orbitals on the basis sets. And then you have this derivative of the basis set with respect to nuclear positions. And then these terms are the Kohn Hamiltonian, the eigenvalues, and again, the basis set. So this is the heart, the core of the Pulley terms. And I would add that if you use any functional that goes beyond LDA, you also have extra Pulley-like terms that come in with GGAs, meta GGAs, and also if you treat the kinetic energy relativistically for the electrons, you have more terms and so on. And all of them have actually been discussed and written down in this original publication of the FHI-aims code. So please have a look if you are interested in that. However, that's really not the full story, because the energy functional, the Harry's energy functional that I showed in a few slides before, this one, has something embedded into it that was not written explicitly back then. So at any point in your self-consistent cycle that you evaluate this energy, you have terms in this Harry functional that are calculated at that self-consistent step, and you have parts of these ingredients that go into this whole functional that have actually been calculated in the previous self-consistent step. So here my self-consistent step is given by these M indexes. So M is the step I'm in, where I'm evaluating this energy functional, and M-1 is the previous self-consistent step. And this is the mixed density in step M-1 that you use to build all your potentials that then go into the conditional Hamiltonian and then are used to get the eigenvalues at that step. So that means that you have this mismatch, let's say, between these terms and what enters this term here. And if you are fully at self-consistent, or as close to self-consistent as you can get, then it's all fine and you don't have any extra terms on the forces and everything's okay. But if you're not quite there, you have a term in the force that comes from this mismatch in the energy functional. And again, I mean, you can deal away with it by two ways. You can do more convergence of your density so that you don't have these terms, or you can calculate these terms explicitly and add them to the forces, so you have accurate forces at an earlier point in your self-consistent cycle. These terms look like what I show here below, so you can derive them as well. So you have here a difference between the mixed density at step M-1 and the unmixed density, so the constant density itself at step M, times this derivative of the Hartree potential with respect to the positions, plus also another term with the exchange correlation potential. So this term here of the Hartree potential, that is the largest one of the two that I show here, has been implemented in FHI-aims now in last year by Ergodic Hypothesis and myself, with a lot of discussions with Basti and Volker and everyone to make the whole thing look nice and restructure the whole SCF step so that everything is nicely calculated. So now we have this term, and I can show you why it makes a difference. So I remind you that we're trying to do Hamiltonian dynamics. So it's so far what you would call the microcanonical ensemble at this point in the talk, right? So the energy should be conserved. And for the energy to be conserved, we have to have consistent forces with the energy that we're calculating, right? So what happens is that this is an old picture that I have in my talk. So this is C2H6, and we're doing MD here. And what you would like to see is that as the time, as you propagate in time, the energy is conserved, right? So if you go into very nicely and tight thresholds for the convergence of the density, you see that at this point the energy was conserved. But if you do cheap settings for this convergence of the density, so you don't converge the density too well, then you have this drift in the energy here, and this is a departure of what is physically acceptable for such systems, right? But how does it look like now that we have this force correction term? So this is a plot from Isaïn that I took. So he did this study. And this is the Zundel cation now, the system that you will work with in the tutorial this afternoon. And we are doing ab initio MD as well. And what you can see here is that the blue points, the blue evolution, which is a much longer time evolution, 10 picoseconds, the blue points, they do not include this non-self-consistent force correction, and they do conserve the energy quite nicely throughout this time evolution. But what is much nicer is that you can use a much looser convergence setting for the density, 1/10 to the -3, and add these non-self-consistent force corrections, and then you get the same energy conservation, which is nice because you don't have to do so many self-consistent steps in your simulation, and you save time. However, it's not a cure for everything. Of course, if you don't converge well your density, you still don't get right dynamics. And if you go a little bit further, 1/10 to the -2, even if you add these non-self-consistent force corrections, you still have the drift. So, you know, it's not that's as far as we can go, but it's a big step forward. Then the second thing that I would like to mention is the importance of the time step. This is also another exercise that we'll do in the tutorial today. So here I have now something that was a movie at some point in the presentation, but is now a PDF, so it's not a movie. So here what will happen is that I will evolve in time the Zundel cation here. These are oxygens and hydrogen atoms, and I'll do the Verlet algorithm that I talked about with a time step of 3 femtoseconds, and I'll calculate forces with ab initio, from ab initio code, so from DFT. Now, you'll not see the movie, but what happens is that in very few steps, maybe 5 steps or so, you'll have this molecule completely dissociating. So this piece will go this way, and this piece will go this way, and the hydrogen atom will go some other way. Okay, so this is the depiction of the movie that is not going to happen. So this time step that I used for the integration of my equations of motion, 3 femtoseconds, which is quite, you can say small, is not enough to make my dynamics stable. So you need to choose a time step that is small enough to make your dynamics stable, right? And how to choose that really depends on the system that you have. So it depends on the highest vibrational frequency of the system. You want to integrate accurately the fastest motions that you have in your system, and that corresponds to the highest frequency of vibrations. So you can make in any system, you can make a quick back of the envelope calculation. If you consider your system more or less harmonic, you know what is the highest frequency of vibration, because it depends on the inverse mass, right? So you can more or less have an idea. If you know, for example, what is OH, you can scale everything by that. And then you typically choose a time step corresponding to 1/10, 1/10 omega max to evolve your system. So for example, for this system, you have to choose a time step of 1 femtosecond or below, because the period of vibration of the highest frequency of vibration is around 10 femtoseconds. Yeah. So that is it. And this is how you do Born-Oppenheimer molecular dynamics. But of course, so you have the time step that is nicely given by what I just showed before. You have to converge your self-consistent cycles well, even if you can correct your forces for some lack of self-consistency in this energy expression, but you still need to pay the price of going over all of these self-consistent steps. And one thing that very early on people realized was, well, wouldn't it be really nice if we didn't have to do all the self-consistent steps, and we could jump all this self-consistent procedure and move everything in time immediately with maybe only one diagonalization of your Constant Hamiltonian? That would save a lot of time. But is it possible to do that in a rigorous way? And Carpardinello Molecular Dynamics wants to do exactly that. So they proposed to do an extended Lagrangian where you have your physical system. So here the kinetic energy plus the potential minus the potential energy, this is the Lagrangian now of your physical system, and you augment that with fictitious degrees of freedom that now depend on these Kohn-Sham orbitals that you see here. By the way, I just noticed this is missing a sum over ij here. And by doing this dynamics, you can then calculate the equations of motion, both for the nuclei as well as your fictitious degrees of freedom, which are involving the Kohn-Sham orbitals of your calculation. So you evolve them explicitly in time with your system. And the key thing to do there is to choose this mu here, which is a fictitious electron mass, small enough in order to get an adiabatic separation of these fictitious degrees of freedom from your real system. So you have to choose mu small enough such that it doesn't, it creates the right potential for which your nuclei are moving in, and it doesn't mess up with the dynamics of your nuclei. So because mu has to be very small, the actual highest vibrational frequency in this scheme is quite high. So you have to use very small time steps to integrate these equations of motion, but you get as an advantage that the electrons follow the nuclear evolution, so you can effectively avoid achieving self-consistency at every step and basically gain time by that. Nowadays, Born-Oppenheimer molecular dynamics is preferred to this standard type of Capernello molecular dynamics because doing the self-consistent steps doesn't cost so much anymore, and dealing with this very small time step that you need here is more costly than just getting the convergence normally for most calculations. However, there are methods that want to do the same idea and don't have the small time step problem. They go into the umbrella of what you might say acceleration techniques for molecular dynamics, and they all involve some type of evolution of your Kohn-Sham orbitals or wave functions, if you like, with your nuclei. So you want a very good guess for the wave function of the next step, and normally you have to ensure time reversibility, which is really a key for the stability of propagation of these schemes. Lots of people have worked on that. I just give you a few references here on the top. I won't go into detail here due to time, but you can either just extrapolate the electronic density and correct for that, or you can also do some types of extended Lagrangian formalisms that also have auxiliary variables that move in some type of harmonic potential around your self-consistent solution, and then you avoid this small time step problem as well in these dynamics. I want to mention so far that some of these techniques have been implemented in FHI-aims, but with limited success, so they are not the default in the code right now, but there are ongoing efforts, and probably something of one of them will be there quite soon. Okay, so I'll take the last 10 minutes maybe of the talk to add a few words about how you can do other ensembles and give you an example of what you can do with them. So the most natural ensemble that we started talking about is the canonical ensemble, but you might be still wondering how you can actually do that, because if you do Hamilton evolution of the equations of motion, you have microcanonical calculations, and I want NVT, so I want to control the temperature of the system instead of the energy. And that's also very interesting for experiments because they're usually done at constant temperature, not constant energy. The idea of how to do that is very simple. You embed your system into a bath that will make sure that the temperature is maintained. And for your system now, the energy doesn't need to be conserved anymore, but for the system plus bath, the energy can and usually is conserved. So one way to do this is to do an extended Hamiltonian or Lagrangian. This is the idea of the Nose-Hoover thermostat. You again have these extra degrees of freedom that you add here to your Hamiltonian or Lagrangian, and they give rise to equations of motion that effectively conserve the temperature of your, impose a temperature in your physical system. That happens because the momenta are damped by this fictitious oscillator that you add here. And one has to be careful with this type of thermostat, because if you use only one of them, because it's a harmonic piston, this fictitious oscillator, not piston, sorry, there's a harmonic fictitious oscillator, the system can get stuck in a region of phase space, the dynamics might not become ergodic, and normally you have to attach a chain of these Nose-de-Hoover thermostats to overcome this ergodicity problem. And this has been realized quite early on in this publication here. So a Nose-de-Hoover chain is what normally you have to use in order to get good temperature control with this type of thermostats. Then there were early ideas of temperature rescaling, like the Berendsen thermostat. You just rescale the velocities by a factor that guarantees that you get to the target temperature that you want to get. It does not sample the canonical ensemble, though, and so you can get the famous flying ice cube effect, in which rotations and translations acquire super high kinetic energy, but the vibrations are frozen. So this is not a thermostat that is a real thermostat. It doesn't sample the canonical ensemble, and it makes your system unphysical. In another quite early development, there was the Anderson thermostat also, in which you do a stochastic change in your momenta of the systems, of your particles in the system, sorry, and you change it to a momenta that is consistent with the Maxwell-Boltzmann distribution at the target temperature. And this is a good thermostat in the sense that it does sample the canonical ensemble, but it's not very efficient, and it's very sensitive on how often you do this procedure. More modern thermostats that you will see in the exercises, they try to get ideas from both, let's say the Berendsen and the Anderson thermostat, or Berendsen, Langevin, stochastic-like thermostats. And there are these stochastic velocity rescaling thermostats, and they have a temperature scaling part and a white noise part. So you have both temperature scaling and random stochasticity in the equations that then rescale your momentum or change your momenta such that you get temperature control very efficiently and in a very robust fashion. It's not really too dependent on what you put here for the parameters of the thermostat, and you can even define a conserved quantity to check whether your dynamics are doing good. As I mentioned already a bit in the previous slide, I mean, this stochastic idea, of course, I mean, you can also use a Langevin equation in order to mimic a thermostat. This is how it would look like. So you have, again, your original system plus friction and white noise. But in this case, the friction and white noise really obey this fluctuation dissipation relationship, in which the white noise time correlation is a delta function here. So there's no memory of past times, and it's related to the friction parameter gamma that you put here. So this thermostat is quite sensitive on gamma, the friction parameter. And it's hard to know what is the best gamma to choose if your system has a wide range of frequency ranges, and also it disturbs the dynamics considerably. But you can get away from these issues of this thermostat by going to a higher dimensional, by solving a higher dimensional problem. So that is the colored noise thermostats, they are called, and they are based on a type of generalized Langevin equation. So you extend your system again with this idea with other fictitious degrees of freedom. So you have a higher dimensional problem now to solve. And you have Markovian dynamics, so this Langevin-like dynamics, in which you have no memory of past time in the extended phase space that you now define by these extra S variables here. And you have now matrices that are doing the job of this friction parameter, and the matrix here also that multiplies this random noise. But this is just random noise here, but not a matrix now. So you have again the original system in friction plus white noise, but in an extended space. And if you integrate out this S degrees of freedom, you have for your physical system something that is not Markovian anymore. What does it mean? It means that the friction term or the friction kernel has memory of past times. And the fluctuation dissipation theorem now looks like this. You have the time correlation of your colored noise now, which is KBT times this memory kernel that you have here. So why it's colored? Because the Fourier transform would not be flat. It would have some structure in frequency space. Okay, few words on pressure control. So if you want to control the pressure in order to then get, NPT, so isobaric and isothermal ensemble, isothermic ensemble, then you have to do something more, right? First, you have to calculate the pressure somehow in your system, and the definition of the instantaneous pressure is given here. This term here specifically is the stress tensor. So calculating this from ab initio, if you have seen those terms in the forces and you said, oh my God, there are many terms in the forces, for the stress tensor, they look even worse, I would say. So in any ab initio code, it's quite a difficult job to write down all the terms that come into the stress tensor and write it down nicely, so you have a proper quantity to put here. But this has been done in FHI-aims by Franz Knuth and Christian Carbonio some time ago, and it's a very nice implementation. And so you can do NPT simulations with FHI-aims as long as you have then a barostat also put in your system. And the idea of the barostat is now that you have, again, the system embedded into something large, your physical system embedded into something larger that now wants to maintain the pressure. So while your system tries to press out, that thing tries to press in so that everything's equilibrated and you get the pressure that you want. There are similar schemes as those for thermostats. There's pressure rescaling, extended Lagrangian, stochastic pressure rescaling, and so on. And in order to fully realize the isobaric and isothermic ensemble, you have to couple the thermostats with a barostat, right? So there's both a thermostat and a barostat acting together in your system, and then you get that. You will have an exercise also that does that today. Today you'll be working with the IPI code. The IPI code is a Python interface for the calculation of molecular dynamics, also for path integral molecular dynamics, which we don't talk about today. And it communicates with the electronic structure code through internet sockets, so it's very flexible. It's interfaced to many electronic structure codes. FHI-aims is one of them. You can check this web page here if you want to know more about the code. I won't talk much more about the code because you will see it in the exercises this afternoon and tomorrow. The slides will be here anyways, so we can skip to one application, which I find quite nice. And this is the final part of the talk, which is actually quite fast. So one application that we did that I think uses several aspects of these molecular dynamics are these calculations of the free energy differences for molecular crystals. This is also related to one of the exercises that you do, calculating free energies from molecular dynamics. And what we wanted to do in this calculation is calculate an ab initio free energy and free energy differences for full molecular crystals like the paracetamol crystal. Okay, so the way we started here is that we defined just the cohesive energy of the crystal. So you have your crystal over, you have the unit cell, you divide by the number of molecules in the unit cell and you take away the energy of one molecule. So you define this first binding energy, if you like, of your crystal, right? And then you want to start adding terms that will make up your full free energy in the end. So at first you can add something like a classical harmonic free energy to your system. And that gives you both for the crystal and for the isolated system a next step and a correction. So it's a harmonic free energy, and classical here means that my nuclei are classical, right? So you know how to do that, because in the harmonic case, you know how to write this term. Then after that, you want to add harmonic corrections. You can do that by a thermodynamic integration. You do that in one way in the exercises this afternoon. Here we did some other way. We defined these anharmonic corrections by a thermodynamic integration over the difference between this real potential, which is here just a force field still, not the ab initio potential, and the Debye potential, which is the potential of the harmonic system. So then you get one more step here. But this is not the end of the story, because as you'll see also in the exercises this afternoon, nuclei are more often quantum particles, not really classical particles, especially if you have these light hydrogen atoms playing a role here. So we're still missing the quantum and harmonic contributions to this whole story here. And this we can get by doing another type of thermodynamic integration with path integral molecular dynamics, in which you then calculate this kinetic energy by path integral molecular dynamics. I should say that in all of these steps, especially for example here in this one, every time I have this symbol here, it means that I had to do molecular dynamics, because I had to calculate an ensemble average, and I did it with molecular dynamics. So all of these only uses basically molecular dynamics, right? And then if I really want to get the ab initio free energies, I would like to be able to do all of these steps as an ab initio potential as well. But this correction between the harmonic and the anharmonic energy with an ab initio potential for such large systems is not really feasible. It's very difficult to achieve, actually. So you cannot do this part here. But what you can do is yet another type of thermodynamic integration, in which you just calculate you do dynamics in which you calculate the expectation value of this potential in the DFT minus the potential in the force field. And then you can jump from this point in the force field to here in the DFT part. And then after that, you can calculate the quantum and harmonic corrections with DFT. They are easier to calculate. So in that way, you can get full quantum and harmonic free energies of binding free energies, if you like, for real molecular crystals. And you can do that for several crystals, and you can look at what happens, which terms are the ones that play the main role here, and which ones don't play so much of a role. For example, if I go each step of that scheme that I showed in the slide before, I am at the potential energy surface. I add the classical harmonic corrections, classical enharmonic corrections, quantum enharmonic corrections for two polymorphs of this paracetamol crystal. You see that the biggest change in free energy here, which is given by the y-axis, happens when I add the enharmonic contributions. And F1 is form 1, F2 is form 2. And you see here, I have the force field in dashed lines and the DFT in full lines. If you look closer at this and you calculate the difference between form 1 and form 2, you see that in the force field, you have form 2 more stable than form 1, and in DFT, you get form 1 more stable than form 2, and it gets more and more stable as I add these corrections to my free energy. This happens to be consistent with the experiment, in which form 1 is indeed more stable than form 2. This is it. I thank you very much for your attention. These are references which you can find a lot of things about ab initio molecular dynamics, and also path integral molecular dynamics in this book, at least. If you're interested in that, that's something you can also do with IPI, but we won't be covering the exercises, and everything else you can look at these books. And thank you very much for your attention.
Thank you, Mariana, for this wonderful talk. So now we have this Q&A session, and everyone is welcome to ask a question. So please raise your hands if you have any question to Mariana. Alternatively, you can also write questions into the chat if you feel that's the better way to ask a question. So, yeah, maybe I ask a question. So, where do I know from when treating particles classically is sufficient and when it's not anymore and I have to treat them as quantum particles? Is there anything, a rule of thumb one can apply? Or, of course, maybe it will depend on the target as well, but like, is there any advice one can give? Mariana, you're muted.
Yes, let me find something here. Yes, there are a few rule of thumbs that you can think about. So one is precisely what is how much 0 point energy with respect to your thermal energy that you have available in your simulation. So, for example, if you have, I try to find a slide here in a second. Yes, so can I share here again now? So you see my slide here, right? So there are two rule of thumbs, basically. So one is that the lighter your particle is, the more quantum you'll expect it to be. This you can see from something like the thermal de Broglie wavelength that you have that I have written here. So this is something that is more valid, like is derived for free particles, right? But it's a rule of thumb that you can think about. So if this big lambda is much larger than your interparticle spacing, then that happens when you have low mass and low temperature. Nuclear quantum effects might be important, okay, because you have, let's say, an overlap between the wave functions of your particle. We could think more or less like that. But if it's instead much smaller than your interparticle spacing, then classical Boltzmann statistics are fine, and you're okay to do that. So you can calculate this number here for a few particles and a few temperatures, and you see that the electron is, of course, quite quantum, right? Even at 300K, you would have 43 angstroms of these de Broglie wavelengths if you could apply it to electrons. So you expect it to be quantum. Hydrogen is 1 angstrom at 300K, so it is quite quantum even at room temperature, you could say. And then the higher your element is, the smaller this thing is, but the lower you go in temperature, the larger it is as well. So copper at 10K actually would be quantum as well as a nuclei. Beyond that, I mean, if your system is actually in a potential, you would like to know more about frequency of vibrations or something like that, because you could think about the harmonic system that is in a potential and so on. And then it's nicer to think about how far from equipartition of energy you are, right? So if you would have your harmonic, so if you can approximate your system by harmonic and you have a bunch of frequencies of vibration, and you could fill all of them with just thermal energy, how wrong would you be with respect to the actual feeling of simply 0 point energy in each mode? Yeah. So if you have quite low vibrations, low frequency of vibrations, then at not so high temperatures, you reach a situation in which the separation between two vibrational states is more or less equal to the thermal energy, then you're classical. And if not, then you're quantum. And then quantum effects might be quite important for you. No. Yes.
Okay, no, thank you. So Raymond raised a hand. Raymond, would you?
Hi, thank you for the talk. I was just wondering, you mentioned the, so regarding the Pulley forces, you said that they are 0 when the basis set is either complete.
Yeah.
But I was wondering if, for example, using like a code with plane wave basis sets.
And then you don't have this problem. Then you don't have them. Because then the basis set don't move when you move your atom. That's the easiest way to say it, right?
Okay.
So if you have plane waves, the plane waves will not follow the movement of your atom. They are defined by the box, basically. No?
And then, so then, oh, sorry, yes.
Yes, and the energy cutoff that you put in all that, right? I mean, it doesn't depend on the positions of the atoms. So then you don't have that term, yes. But for FHI-aims you do, because you don't have plane waves. That's
Okay.
the point. And what I meant, but in that slide, is that if you had this atom-centered basis set, but you could dream of having the complete basis set, then you would also not have these terms even for atom-centered orbitals. That's what I meant. But you never complete. So it's.
And then for a code which would use, for example, a mixed basis set, how would that, I guess, to take the best parts of both worlds, so to say?
I am not an expert on that. I think you have those, I mean, you have to be very careful. I think if you mix the basis set, I don't know. I don't want to say anything here that is wrong. But you might even have more terms,
Okay.
because then you mix two things. I really don't know.
Okay.
Maybe someone else can comment, but yeah.
Thank you.
So further questions?
Hello.
Abdeslam, yes?
You hear me?
Yes, we do.
Hello, everybody, and Happy New Year for everyone. I have just a small question about molecular dynamics. When you do it in microcanonical ensemble, the final stage that you reach, is it just an equilibrium, or the ground, or you are doing a ground state calculation? I mean, how to do ground state calculation in the microcanonical ensemble?
Ground state for what? Like for your electrons, or for your
electrons and atoms, or electrons and nuclei? I mean, what different what we know in other codes, like what we call optimization, structural optimization.
Ah, I see. Mm-hmm. Mm-hmm. So I think you mean whether I will find the global minimum.
Yes.
Of my nuclear structure, right? Or not. So in principle, you could, okay, with microcanonical dynamics. But it's not guaranteed that you will, right? I mean, because you might get stuck in a region of phase. So but yes, I mean, so if you would do microcanonical dynamics, and you would, let's say, progressively freeze your momenta, so take out velocity from the system, okay?
Yeah.
It actually, you can show it mimics, I think conjugate gradient.
I mean, instead of doing conjugate gradient, which is just a minimization technique, I mean, is it possible to do a damped molecular dynamics? To add
yes, that's what I mean, exactly. But I mean, yes, and you can do that. I mean, whether it's better or worse for your problem is another question. You know, because if you have to do it in this way that you have to slow down the system. Basically.
Yeah, you freeze the system to the ground state.
Yeah, exactly.
What are the techniques that are implemented in FHI-aims to do such calculations?
So FHI-aims has geometry optimizers that are quite good, right? So it's if you want to do a geometry optimization, normally you're better off doing an actual geometry optimization, unless for some reason you want to do this trick. Yeah. So FHI-aims has many geometry optimizers built in. The most used one is BFGS with the trust radius method. And yeah, so
and these techniques are not molecular dynamics in principle.
Not what one calls molecular dynamics normally, no, because you don't, the geometry optimizer doesn't involve time evolution with Newtonian dynamics.
But forces are there.
Yes, but it's just a algorithm to minimize based on the gradient of your potential energy, right? So it's
okay.
So maybe I can also comment on that. So if you know roughly the minimum of your structure, then like using a BFGS is like the best way to go. If you don't know, if you have the feeling you have to sample your potential energy surface to find maybe another minimum, then you can use like something like is called FHI or MDmin. And this is implemented in ASE. I'm not sure if you heard about it. It's basically this one here, ASE. And this can, ASE can operate similar to IFI. It can thrive FHI-aims and through an internet socket. It's basically the same implementation as IFI, as was implemented by the IFI developers. Mm-hmm. And if you use ASE, you can use like other optimization algorithms, which make use of this kind of dynamics.
Okay, I see.
So it's not directly implemented in FHI-aims, but you can use ASE without any computational overhead in the optimization, basically.
Okay. Thank you very much.
But so BFGS is a bit a different family, right? So.
Thank you. Thank you.
I would say, is there any question left over which we can answer? If not, then I would thank Mariana again and stop the recording.